So, our next speaker is Giuliano Giudici.
1, 2, 3. Sì.
Un po' sul collo, ma non abbiamo niente.
Oh, 3. Hi, everybody, and happy birthday, Professor Caracciolo. I wanted just to tell this very brief story about the fact that I attended your theoretical physics classes, you might remember, but I just checked the picture and I wasn't there. I don't know why. But then I remember that after I attended your class, I went to the, to SISSA to do the master thesis with Professor Mussardo. And I remember I made you very angry about the fact that I didn't send you the summary of my master project before submitting it. But then I asked my girlfriend if she could bake some cake for you, and I came to you with the cake for asking for your forgiveness. And that's something that I remember very well. I hope you enjoyed it. I'm sorry that my talk is not really about statistical physics, but yeah, I hope you'll enjoy it anyway. I'll try to be very quick because we are very close to lunch. As you can see from the title, it will be about Rydberg atom arrays and how to use them to make quantum simulations of topological matter. As I don't have much time, the outline is very brief. I will introduce you very quickly to how to make quantum simulation with Rydberg atoms. And essentially, I will write down the Hamiltonian, which will be the subject of the rest of the talk. And then I will tell you a little bit about the most recent developments on how to realize quantum spin liquid states in this kind of systems. And hopefully I will manage to get to the end where I will discuss quickly one of my contribution to this field. So let me directly start from the Hamiltonian. Rydberg atom array is just an array of atoms where you have optical control on 2 levels. One is, you can think of it as the ground state of the atom, and the other one is very highly excited Rydberg state. And you essentially can control the amplitude of a coupling between these 2 levels by just tuning the, by changing the laser power. And there you can tune a little bit the frequency of the laser of resonance such that you have the tuning with respect to the energy difference between these 2 levels. And you end up with an Hamiltonian with these 2 terms here. One is just controlling the rate of transition between these 2 levels of the atoms on each side of a lattice. And the other one is essentially tuning the density of excited atoms in this lattice. In this case, I draw a 1-dimensional chain. And the way these atoms are arranged into this chain or into whatever 2-dimensional geometry you can think of is by optical tweezers, which allow for a very high level of manipulation of the lattice geometry. The most important thing of this Hamiltonian is the interaction between 2 excited Rydberg states. And given the fact that the excited Rydberg state is really highly excited, the atoms behave like very large dipoles, which for particular Rydberg states take the form of this 1/r⁶ potential, which allows to introduce an extra parameter in the Hamiltonian, which is called blockade radius. Essentially, since the interaction is very strong for for distances between the atom below this blockade radius, which is defined by this equation, and which is essentially set by the laser power and by the distance between the atoms. You essentially treat the potential below the blockade radius as infinite, and you have what I call the interaction-induced effective constraint, which is totally tunable experimentally. And this essentially gives rise to a constrained many-qubit system, which can be put on 1- or 2-dimensional setups. And it essentially prohibits the simultaneous excitation of two Rydberg atoms. If you want, you can think of this just a spin up and spin down. So you can't have two spin up within the blockade radius, and this gives a constraint to the states which matter for the dynamics and the ground state of this Hamiltonian. Yeah, and essentially this system has been widely studied in one dimension in the last like 4 to 5 years, both experimentally and theoretically. And this is a sketch of a phase diagram as a function of this parameter, the blockade radius, and the tuning, which is controlling the density of excited Rydberg states. And you see that there are a lot of phases in this phase diagram. And the people who were studying this system theoretically focused a lot on understanding especially the universality classes of phase transition between these phases. And they found there is a very rich phase diagram with CFTs describing, the critical points, but also with some region where the phase transition was not really well understood in terms of conformal field theories. And I also contributed a little bit about this during my PhD. And then another very interesting topics that people realized in this model was to study the dynamics of simple initial state, which was not satisfying the eigenstate thermalization hypothesis. And in the beginning, and I think all of you know what I'm talking about, but essentially this is the dynamics of an observable, which was expected to thermalize very quickly, whereas it was oscillating very wildly for apparent no reasons. And then people realized that this Hamiltonian has very atypical eigenstates in the middle of the spectrums, which have been called many-body quantum scars. And a lot of people started studying this model exactly because of this reason. And then they found this atypical eigenstates in other model, and so this became I would say a very intense field of intense research activity. But what I want to talk about today is about two dimensions. Yeah. No, that's actually unrelated, and that's one of the things that people are trying to understand is whether these quantum scars have any relation to integrable systems, and it seems that so far the answer is no. There's no conserved quantities, other than the energy in this Hamiltonian. But I would say it's an open problem, and there might be connection in specific cases, but generally speaking, no. So today I want to talk about 2D systems, and here is an example of this Hamiltonian, which is always the same on the square lattice. Again, here we have the blockade radius, which is increasing the radius of the constraint for which you can't have more than one excitation inside the radius. And here again is the parameter which tunes the density of Rydberg excited states. And you see that at large density, which is like on the right of this phase diagram, you have a lot of phases. And of course, phase transition. These are results for simulations on this two-dimensional square lattice. And the point is that all these phases are actually, you can think about them as classically ordered phases, in the sense that, all the ground states of this Hamiltonian here have a product state representative, and they just like they are certain pattern of symmetry symmetry breaking. Now, the question that I would like to ask today is there a way to engineer any sort of quantum order in this system? And if yes, on which lattice geometry? And the phases that I'm looking for are what are nowadays called topological states of matter. And in particular, since this is kind of a spin system, I'm looking for quantum spin liquids, which are just states where there is no symmetry breaking. So they are like liquid, like in this picture here, but they are characterized by something which distinguish them very much from trivial product states. And indeed, they are characterized by topological ground state degeneracy, which does not arise from any symmetry breaking, and by long-range entanglement, which you can spot if you compute the entanglement entropy and you check violation to the area law of entanglement via this constant contribution, which is called topological entanglement entropy. And then there are non-local excitations, which are created in pairs. And there are emerging gauge fields, which allow you to describe these states of matter and many other properties. But the reason why they are interesting from a theoretical point of view is because, well, first of all, they are novel, fascinating quantum phase of matter, but also because they have several applications in quantum technologies, such as topological quantum computation and quantum error correction. So let me try very briefly to understand why on the square lattice there is nothing like those states. Well, if you now consider only this Hamiltonian no interaction, because I'm already assuming that there is a hard constraint at this radius here, which means I can't, excite two Rydberg atoms close to each other within this radius. And now imagine that I'm at very large density, so I'm switching off this term here. And if you think about what are the ground state of this Hamiltonian, they're just these two, two checkerboard patterns. Which of course break the Z2 translation symmetry of the lattice, because you can transform one into the other. Now, what happens if you add quantum fluctuations to these states here? Well, you just get a spontaneous symmetry breaking quantum order, which is a little bit dressed, but still it's nothing special. We have already in the classical world. Now, the idea to get something which is less trivial is to put these atoms onto a lattice which has a very large number of highly degenerate, very large number of classical ground states at large density. And one way to achieve this is to put the atoms on the links of a Kagome lattice. This is not my idea, of course, but and if you fix this blockade radius like this, you have mapping between the Rydberg atoms and dimers on the Kagome lattice. And if you try to check how many are the configurations in which you cover your Kagome lattice with dimers, such that you have a dimer entering each vertex, you see that they are a lot. They are exponentially many. And now, if you add quantum fluctuations to this manifold, you might hope there is something like this state here, which is the equal weight superposition of all these dimer coverings. And this is called resonating valence bond state. And it is known to be a topologically ordered state, so a quantum spin liquid, with a form of topological order, which is called Z2 topological order because of a certain local rule which is associated with this configuration, which is nothing but having one dimer entering each vertex. Now, let me show you some numerical simulation that I did. They're not coming from this paper, but they are kind of very clean. And since you have an hard constraint on this system, you can just simulate, directly compute the ground state of this Hamiltonian exactly on this very large cluster of sites, which is taken periodic in all the directions. So imagine that you identify this with this, this with this, etc. Now, if you compute the ground state of the Hamiltonian, you immediately see that you have like two-phase transition. This is just a witness of the fact that the ground state is changing very rapidly from the high density to the low density regime on the right. And you see that you have like three phases. And as it turns out, the phase in the middle is indeed a quantum spin liquid, which is characterized by the fact that the ground state has the overlap between the ground state as this and this RBB state that I showed before as a bump here in the middle. So the thing is, this phase, it turns out to be topologically ordered in the sense that I meant before, but the ground state is not really exactly the RBB state, as you can see from the overlap here. It's large, but it's not one. And the reason is that in the Rydberg Hamiltonian, you have defects on top of these dimer coverings. So if this, you remember, a dimer is a Rydberg on the link of this lattice. And the reason is that, the quantum fluctuations are not only building up this equal weight superposition, but they're also lowering the density of atoms, right? Because, if you check what is the density, sorry, of excited Rydberg state, so of spin up, if you want. And but still, they realized the experiment in this Hamiltonian, and the idea was to exactly reproduce this kind of phase here. And but the point is that experimentally they can't compute the ground state. So what they actually do is they dynamically prepare what they would like to be the ground state of this Hamiltonian by starting from a product state which is easy to prepare. In this case, the starting state is the state where all the atoms are in their ground state, which is what I called here like 0. And then they switch on the coupling in this Hamiltonian, and they tune them to the regime where they know there is a topologically ordered phase. I mean, these are just experimental data, which I'm not going to explain, but just trust me when I say that these kind of bumps in these parameter regimes are signaling that there are all marks of topological order. Of course, these are experiments, so nobody can really theoretically prove that this is rigorously a topologically ordered state, but it's something which is close to what they wanted to observe. So in the very last part, I would like to tell you what I tried to do, and the idea was to first of all try to see whether the experimental preparation protocol could be optimized to obtain the pure RVB state, which with no defects. And the reason for this is that that is the state with the shortest correlation length. I mean, if you add defects on top of the dimer coverings, you increase the correlation length, and perhaps you spoil the topological character of this state. So the second goal indeed is to understand whether adding defects does spoil topological order or not. And the way I did that very briefly is just by devising a protocol of experimental preparation in which you first turn on this laser power here, and then you increase the density by turning on the what I call the tuning, which is just favoring excited Rydberg states in the lattice. And I showed that you can indeed optimize a lot the overlap between the finally prepared state after this dynamical protocol and the pure RVB state, so the RVB state with no defects. And here you can compare it, for example, if you check what happens to the ground state, it has an overlap, which as I showed before, it's much, much smaller than this one, which is the overlap with the final state as a function of the total time of the preparation process. And the idea is that if the total time is very, very large, you are going super, super slow, and you are essentially staying in the ground state. Whereas if you go super fast, you just, excite a lot of Rydberg atoms. There is a sweet spot in the middle for which you can get this overlap optimal. And the optimal time actually scales linearly with the number of atoms, which is not so bad because it could have been much worse from an experimental point of view. The second result that I got is that I managed to describe this RVB state with defects as with this two-dimensional, two-parameter ANSATZ, which is very simple. And it's just the clean RVB state with some operators which are local and destroy the dimers locally. And these essentially are the meaning of these terms here. I'm not, how much time do I have? I'm late. I think so. So I will skip this description. And this plot is just to show that during the dynamical preparation process, this state here actually described perfectly. This is 1 minus the overlap of a dynamically prepared state and this optimized to parameters ANSATZ. And the other cool thing is that this state is a tensor network state. And since I think not all of you are familiar with this, let me just briefly tell you what tensor network states are. So essentially, you can decompose the coefficient of a generic quantum state as product of matrices in 1 dimension or tensors in 2 dimensions. And the idea is that in 1 dimension, this decomposition is very efficient to provide variational ANSATZ for ground states of local Hamiltonian. Whereas in 2 dimension, the calculation of expectation values is not super easy But there are controlled approximation schemes, which are the schemes that I've been using to try to understand the properties of these two-parameter variational ansatz. And so what you can do is you can really say, okay, I know this state is perfectly describing the dynamical preparation protocol of the experiments, but do we know if it's topologically ordered or not? So what you can do is you really study the two-parameter phase diagram of this state here. You just study the properties of this state. And you realize that there is indeed a topological phase in this corner of the two-parameter phase diagram of the state. And you see that the optimal parameter that you get from the optimization are indeed inside this topological phase. And this is sort of like a theoretical confirmation of the fact that you can have topological order with defects. And so what they observed experimentally might indeed be this state here with rigorously proven topological order. And now I'm ready to conclude. So I tried to tell you that you can indeed realize topological quantum spin liquids or something very similar experimentally with Rydberg atom arrays. And you can also try to remove defects from this finite density quantum spin liquid by optimizing the preparation protocol. But even if you add those defects, you might have topological order if you stay in the right corner of density of defects on top of the state. With this, I thank you for your attention, and I hope I'm not super late.
So why didn't the electromagnetic field appear? If you have transitions between two levels, then light will be emitted, but it didn't seem to appear in your discussion.
Sorry, I didn't get the last sentence.
Well, there was no sign of the electromagnetic field in your discussion.
Yeah, because there is that from what I'm not an expert in quantum optics, let me first say that. But from my point of view, this is the effective Hamiltonian that you get after you do the usual quantum optics approximations, and this is the model that the experimentalists use. I know because I know them, and the atoms are in a lattice, and a laser is shined, and this is the Hamiltonian you get. And this is what they can measure.
You see, that's another point which always perplexes me. We don't know the Hamiltonians of these systems. So people write down these idealized Hamiltonians, but then you should check that the results are stable when you start to modify your Hamiltonians a little bit. There should be a principle of universality involved, that the results do not depend too much on exactly which Hamiltonian you use.
No, but I agree. So the point is on the time scale where which they care about, this Hamiltonian is giving you the right dynamics, and if you do full simulations including, but like this is not what I normally do, but I know of theoretical line computed from this Hamiltonian which match the experimental data.
Well, I give up.
But I think I'm not in the position of understanding your skepticism about the Hamiltonian.
So yet again, a way of twisting your model. So you said that an important ingredient is that you have this large degeneracy in the ground state of the effective diamond model on the Kagome. And then you say, and then you have monomer defects and so on and so forth. But then you said at the beginning that this is a result of having approximated a potential that was in fact roughly 1/r⁶ into a 0,1 potential. This approximation is crude, especially.
Yeah, I know indeed. So part of the paper is devoted to understanding also the effects of 1/r⁶ interaction. But the idea is that it seems that for most of what I was saying, it doesn't really matter. Then, of course, you should consider the whole potential to, fit the experimental
Exactly.
data.
So I don't know if you agree with me. The first correction that you would have in this statistical mechanics of dimers would be a dimer-dimer interaction that depends on the relative orientation of the next to next. A dimer will have a certain interaction with the next dimer depending on the mutual alignment, because the true distance will have some.
Well, actually, if you like check really the geometry of this system, the next nearest neighbor interaction doesn't leave the exact degeneracy in the dimer subspace, but the next to next beyond the exact blockade, it's just a geometrical fact. But then the next to next does. It's very small if you tune your blockade radius, but it matters, and that's one of the things we have been worried about, and we try to see how much. And I mean, there is a lot of things that I didn't tell you, but you're right. It's a very crude approximation. But for example, also in the dynamical features like of many-body quantum scars, they did the same. And like you see that they arise anyway in the exactly constrained model. So it seems that depending on what you care about, there's a lot of features already encoded in the exactly constrained model, which is the main subject of my work, but still it's a crude approximation. I agree with you, but most of the things sometimes are there.
So we thank our speaker. Hold the out. We are a little late. But...
Is it on? Okay, so if I understood correctly, there is no simple limit in the model Hamiltonian where the RVB state is the exact.
No, there isn't.
So is it known? I mean, is it known what is the, say, a simple parent Hamiltonian for the states and
the RVB state? Yes.
For the RVB, yes.
Yeah.
And can you?
Yeah, but you don't get it from the Rydbergs because it has a little bit non-local terms that you might say
non-local.
Yeah, non-local in the sense like for I think it's 6 dimers. You have to take a star of the Kagome lattice, and you have an operator defined on the star, and that's the parent Hamiltonian.
Has anybody tried to realize this state by engineering the Hamiltonian, for example?
No, because it's like it's like the toric code. You don't really do that because even if it's just 4 sites, it's hard to make it. And this state is just more complicated.
So we thank all the speakers.